This recording? Is this recording? It would appear so. So if we go to PowerPoint, just go to it. Bloody hell. This one. Greetings, physics students. This is your lecture on electric fields. Some of you have seen this already. If you haven't, enjoy it. Now, electric charges can be positive or negative. Negative is generally an electron. In fact, it's always an electron. And positive can be a proton or a positron. Two charges experience a mutual force in a line between them, just like gravity working between two masses in space. It'll go from the center of one mass to the center of the other. So in this case, we talk about point charges, from the center of one point charge to the center of the other. Now, if you've got these two here, negative charges, they're going to feel a repulsive force between them, so they're going to move apart because like charges repel. Same goes for positive charges. They're also going to move apart, but if you look at a positive and a negative together, well, they're going to attract. And so they are the two possible states that you can have, the two possible directions when we're talking about force applied by an electric field, and that is that the charges will be repulsive or attractive based on those forces. Now we got Coulomb's law that comes in here. The force between two charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. And there's a couple of key points here, and I'd point out directly proportional and inversely proportional to the square. They're key things here because physicists love proportionality, and it gives physics an opportunity to ask you questions about proportionality which don't involve figures, so you have to figure it out in your head. You can't just punch the numbers into a calculator. It doesn't work that way. From this point on, we're going to talk about point charges. So even though you could have a sphere and there could be electrons all over the outside of it, we're going to talk about just going from the center of that sphere. So we'll work only from that center of the sphere around here and not anywhere else. So all charges in this section will be point charges from now on until otherwise told. Now here we can see Coulomb's formula at work. Let's use blue. That should be nice and easy to see. We made a comment before, I made a comment, that force is directly proportional to the charge on one or the other. Just like a planet, if you suddenly double its mass and it's going to have more of a gravitational effect, it's the same with charge. In terms of distance, though, it's different because it's an inverse square proportionality. So it's not just if you double the distance, you're going to halve the force. If you double the distance, you're going to get a quarter of the force because 2 squared is 4. So you must factor that in. We have Coulomb's formula here, and we're looking at 1 on 4 pi epsilon 0 being the constant, Coulomb's constant. That's just 9 by 10 to the 9, and you never need to remember this stuff. It's on your physics formula sheet. So whenever you get a question relating to the use of Coulomb's law, what's affectionately called by the SACE board plug and chug, I prefer plug and play because of the connotations. Anyway, you enter a charge here, and you square the radius. Common mistakes is when you're dealing with nanocoulombs or millicoulombs, not putting by 10 or microcoulombs by 10 to the minus something, and also not squaring the radius. Okay, I think that's enough, so let's move on. This is great because the answers just come straight up. Question: two identical charges Q are meters apart. The force and the repulsion is F newtons. How does the force change if one of the charges is doubled? Well, it's a direct proportionality. So if you times 2 by one of the Q's there, then the force will also be doubled through the whole direct proportionality thing. Now, what would happen if the sign on one of the charges is changed? And I don't think I actually stipulated. So they're two identical charges. Alright. The force of repulsion, yeah. So they're either both positive or both negative, and they've got a force of repulsion. So if the sign of one of the charges is changed, then it's going to be an equal force, but it will now be attractive. And the distance between the charges is doubled. Well, the answer to that is it's an inverse square arrangement. So if you double the distance between them, the radius between the charges, 2 squared is 4, then you get a fraction of 1 on 4. So it's going to be 1/4 of the original force itself. Here's an example of a plug and play Coulomb's law in a let us try arrangement. A charge of +5 microcoulombs is 10 centimeters away from a charge of -8 microcoulombs. Calculate the force between the two. Now you can already see that you've got a positive here and you've got a negative here, so it's going to be attractive. But the thing about Coulomb's law, and often when you see this written online, they'll have these little lines that sit here, 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 and here, and what they mean is that you just put the magnitude of the charge in there. You don't bother with the signs because you're already able to tell if it's repulsive or attractive. So I've got an eraser here. Erase. Excellent. Now if we look here, we have your 9 by 10 to the 9 coulombs constant, and then you just simply enter in your 5 microcoulombs and your 8 microcoulombs, and the key part here is that the distance, the radius between them is in centimeters, often done to check if people are paying attention. So you've got to make sure that you change this to meters, and you've got to square it, which will then give you 36 newtons. Helpfully, I rated these slides from Darwin High. They've made their answer one significant figure in that they've rounded to 40 newtons. That's not the answer. Let's take 36 newtons attractive. Right, superposition. The thing about Coulomb's law is that it represents vectors, and of course you can have more than one vector. In fact, you can have 2 or 3, and then it makes a right angle triangle because that's all physics is anyway. So when 3 or more charges are present, each charge experiences a force due to the charge of the others, the field of the other ones, and the resultant force in each charge is the vector sum of the forces due to the other charges. Now here, this vector sum, we're back to motion in 2 dimensions here. You're going to have that whole, you're going to have an up-down bit, and you're going to have a left-right bit, and you work it all out, and then you end up with another bloody right angle triangle, working out the magnitude of that and what this angle is, or probably that angle, and yeah, that kind of stuff. So let's have a look at an example here. In this example, we've got a charge Q1, Q2, and Q3, and we are looking at the charge on Q2, which is here, as a result of Q1 and Q3. So it's going to be attracted to Q3, but it's going to be repulsed by Q1 because these are 2 positives and this is a positive and a negative. So you've got this pushing down vector here and you've got this attraction vector here. Now I understand that this will change because of course the closer Q2 gets to Q3 as it moves, based on the inverse square, the force is going to get incrementally bigger. So it's going to end up curving around Q3 to a certain extent. But we're talking about what is the force right here at this femtosecond right now. What is that force? And so that's what they're trying to work out. So you've got the vector of the force due to Q1, and then you get your force due to Q3, and you get yourself a resultant force in Q2. Now, here's another example. Let us try. The 2 charges Q1 and Q2 of magnitude +2 microcoulombs and -1 microcoulombs respectively are placed 50 centimeters apart in a vacuum. So Q2 and Q1 are here and here, and they've been placed 50 centimeters apart in a vacuum. There's one and there's the other. Now that's a positive and that's a negative, so that's going to be an attractive force. A third charge, Q3, of magnitude +3 microcoulombs, is placed 40 centimeters from Q1, which is this side of the triangle here, and it's so as to form a right angle triangle, as we see. Now, a part of your knowledge is that if you've got a 3, 5, 4, or what's normally referred to as a 3, 4, 5 triangle, it's 90 degrees, with the 90-degree angle occurring right there. And you have to know that a 3, 4, 5 triangle is a right angle triangle, and any variation of 3, 4, 5, any ratio of it, is a right angle triangle. Now, what do we work out? What's the question here? A third charge, so yeah, fine. Calculate the force in Q3 without showing you too much of the examples. Alright, I want you to use Coulomb's law, so F equals 1 on 4 pi epsilon 0 Q1 Q2 on R squared. I want you to use this formula here to work out first the force on Q3 due to Q1. So this is going to be a repulsive force with a 3 and a 2 microcoulombs, and it's going to go that way. And then your force on Q3 due to Q2 is going to be an attractive force, and it's going to pull up that way. So you are going to end up with something going that way and something going that way, and I assume that means that the vector is going to end up going somewhere up there. I got that right, I assume. Yep. So you've got two different force vectors you need to work out. You need to use Coulomb's law for here and for here, and then make a new right angle triangle and determine the hypotenuse with an angle. Pause the video, have a shot at that.